previous module we derived the state space representation, right, from first principles. So, we started off with a linear time invariant model given by a transfer function. For the p equals q case, we analyzed the signal flow graph, we defined the state variables and we formulated a state variable model in terms of your ABCD parameters relating the input and the output, right. But one of the questions we have to ask is the state space representation unique? Our intuition will tell us probably it is not, because you can define your state variables at different points in a different way in your delay line, and accordingly you can have a different representation. Intuition will tell us, but we will prove it rigorously if it is unique or not, right. So, for any invertible P by P matrix T, we can form a different state representation. So, what we do is, let us suppose W is some t times z. I am omitting the vector notation here, I mean with a slight abuse of notation, we can say this is z and I can put a n here. This is very precise. I would say with slight abuse of notations, I will say W is basically t times z, but W is a vector, z is a vector and T is a matrix which is a P by P matrix and it is invertible. Okay. So, let us define it in this form. Now, going through the previous equations, we have Wn plus 1 is basically T times Zn plus 1, which is equal to A times Wn. Wn is T times Zn plus some vector B times Xn, right. We just are replacing Wn with T times Z of n, and we are writing Yn equals some C transpose times Wn is basically T times Zn plus some D times Xn. So, whatever is before Xn, that remains the same, that does not change, only the variable W will change because it is linked with Z through this transformation T. Okay. Now, we will rearrange, let us call this equation 1, let us call this equation 2. We can rewrite this equation 1 in a slightly different way. So, when we do that, what really happens is as follows, right. You see, just Zn plus 1 is basically we pre-multiply equation 1 by T inverse, and since it is an invertible matrix, T inverse should exist, right. So, therefore, it is T inverse times A times T Z of n plus B x of n, and Yn remains the same. There is a T inverse here, which is basically T inverse times Bxn, and I will call this say equation 3, and Yn is basically C transpose T Zn plus D times Xn. Now if I ask you for the state variable representation of this system where W and Z, which are two different state variable representations, are linked via the transformation T, the parameters are as follows. So, your A tilde, B tilde, C tilde and D tilde will now be T inverse AT is going to be T inverse B, right, and then we said C transpose is what we had. C transpose is basically now T transpose times C and then D. So, our original parameters that we had as A, B and then C transpose and D are now in this form, linked via transformation T. Right. Now, if you ask the question, how many such possibilities of invertible matrices can you find? Infinite, right. So, therefore, what can we conclude? State variable representation, is it unique? It is not unique. So, that is the take home message. State variable representation is not unique. And a trivial invertible matrix is the permutation matrix. So, if you just think about a permutation matrix, it is an invertible matrix, and a good example is suppose I have an object ABC and I permute this object by B, C and A, right. What is the 3 by 3 transformation that can take you from this object to the other object, right. So, here is what I would do, right. If I want B, C, A on this side and I want to link this via a matrix to ABC. So, I basically grep B out first, then I want C, then I have A. This is a linear transformation that can take ABC to BCA, which is a permutation, right, and this is an invertible matrix. So, which clearly tells you that if we permute the state variables, we get a non-unique representation, and this is really a trivial transformation. It is one of the trivial transformations. Okay. So, that is an important parameter. Now, if I ask you another question here, which is what characterizes the similarity between various state representations? Well, we studied just recently that state variable representation is the state space model is not unique, right. But what characterizes the similarity between various state representations, and that is precisely the eigenvalues. And if you invoke the similarity transformation, that is what it does, that is what we did. Okay, your modes should be the same no matter what. So, this is a very important step, and I think the take home from this state variable representation are a few salient points which I want to bring to your attention. The first point is state variable formulation and definition of a state vector. This need not be unique, because we saw in various ways how we can make this non-unique using similarity transformations, right. So, definition of state vector. So, once we formulate the state variables and we define the state vector, then we can derive the transfer function, and once we derive the transfer function, using state space model, we can analyze the dynamics for various forcing functions or various inputs, which is very important. Otherwise, if you were to go the algebraic route in trying to formulate all your equations and derive things, you will be struggling around. So, therefore, it is very important to formulate the state space model, and then once it is ready, you can plug it into your favorite simulation setup and you can exercise to figure out the dynamics of the model. Okay. And the last take home message is the state space models are not unique, and the similarity of various state space representations is through eigenvalues, and therefore, it is coupled via the similarity transformation. So, this completes the module on state space representation.